Hey all, welcome back for the second half of Chapter 2, where we're going to continue our conversation of kinematics and develop our equations of motion, as well as discuss the acceleration due to gravity. So, quick kind of side note. We left off last time after introducing position, velocity, and acceleration and the slope relationships between them. We had the definitions shown here on this page. And as you recall, I mentioned that displacement, velocity, acceleration are all vector quantities. Now, in this chapter, we're only dealing with motion in one direction, either the x direction or the y direction, horizontally or vertically. So what I'm going to be doing from this point forward is I'm going to be dropping those arrows, those vector notations. Now keep in mind, we're still dealing with vectors. They're quantities that have magnitude and direction, but we know the direction since we're only moving in one dimension, and so just a positive or negative is all that's necessary to describe the direction, either forward or backward. So keep that in mind. Also, just kind of a side note, you're going to see this here in a minute, but remember this equation. This is the equation for acceleration, change in velocity over change in time, right? Or the derivative of velocity with respect to time. We're going to be solving this for velocity, doing just a little bit of algebra as we develop our first equation of motion here in a second. But before we do, I just want to make sure we're all on the same page. We've learned about really 5 main kinematic variables that we're going to be using all semester long. The first is displacement, the second is acceleration. Now acceleration can vary, as we'll learn throughout the semester, but for now, for chapters 2 and 4, we're going to make the assumption that we're dealing with either an average acceleration or a constant acceleration. So keep that in mind. Everything we're dealing with now is assuming constant acceleration. That will change as the semester goes on. All right. We then have final velocity, we have an initial velocity, and the elapsed time, instead of doing t minus t initial, we're going to redefine t initial as 0 for us. So the elapsed time will just be the variable t. So from these, we can develop a series of kinematic equations, assuming acceleration is constant, that we get to use all year long. So look at this, get excited, boy howdy. This is basically a party of physics that we're about to have with these equations of motion. So assuming constant acceleration, our first kinematic equation of motion that we will be using all semester is solving acceleration equals change in velocity over change in time. We rearrange and solve it for final velocity, and what we find is final velocity equals initial velocity plus acceleration times time. Now notice I have subscripts of x here, so we're assuming that we're moving just in the x direction. But you could take this exact same equation, replace all those x's with y's, and assuming we're only moving in the y direction, this equation would be the same. The second equation of motion now is derived by just simply taking the integral of this relationship. For those that have taken calculus, the integration should be pretty familiar to you, but if you integrate this, knowing that velocity is change in position with respect to time, what we get is our second equation of motion that tells us position as a function of time, position final equals initial position plus initial velocity times time plus 1/2 the acceleration, which is constant, times time squared. So those are our first two equations of motion. The third, if we were to substitute these two together to try to remove time, so maybe solve one for time and substitute it into the other, we would get our third equation of motion, which relates final velocity to initial velocity, acceleration, and change in position. One pattern you're going to notice, each of our equations of motion only have 4 of the 5 variables. So it makes it a really nice way to isolate different variables. So as you see here, this one doesn't depend on displacement at all. So if you don't know anything about displacement, maybe you want to find time and you know the other variables, this is a go-to equation for you. Now this one that we just derived doesn't involve time. Maybe you don't know the time, you want to find the displacement. Well, this would be a good way to go. So you're going to have to strategically choose which equation of motion to use. And the fourth one, probably one that's used a little bit less frequently, actually just comes from our understanding of velocity. This just says displacement is equal to average velocity times time. So again, the average being the final plus the initial divided by 2. So these are our 4 equations of motion. They're on the master equation sheet you can see at the top of Foxtail. Get used to them. You'll be using them all semester long. And just as a side note, I do allow you to take an equation sheet into your exams and quizzes with you. So be prepared to have these on an equation sheet that you'll be using. All right, so you're going to be using this for a lot of different problem solving. You get to deal with it on your homeworks and workshops, again, all semester long, and especially here in the first few weeks. So how are you going to use these ideas and equations? Well, I want to walk you through the problem solving strategy. Every problem should always start with drawing a picture. You'll either be provided with one or you need to draw it. As you do so, you need to make sure you know what is positive, what is negative. Draw X and Y axes if necessary, but have a picture. I have been known to take away points on people who get problems completely wrong if they do not include a picture, because you must get in the habit of doing that. Second thing, once you have a picture, write down what you're given and what you're looking for. Third, you choose which equation of motion or equations you want to use. Sometimes you're going to have to use a system of multiple equations and solve them together, but try to choose any equation of motion that will help you isolate the variables you're looking for. And once you solve those equations, you will then go back and double check your answers to make sure you haven't made any mistakes. So let's go ahead and give this a try. Here's a first example problem for you. We're going to do a couple at different points, and if needed, I'll make additional videos for you all, really focusing on me demonstrating to you how to do the problem solving process. So let's imagine that we have a jet that accelerates or needs to accelerate up to 62 meters per second in order to take off. So let's say, we've been hired by the Navy to help them design their aircraft carriers. Their jets need to reach a speed of 62 meters per second in order to be able to take off. All right, the maximum or the average acceleration rate, let's say it's an average, is 25 meters per second. So they're asking you, what is the shortest possible distance of the runway on top of the aircraft carrier? They're trying to save money by making these as economical as possible. So that's the problem. Pause the video, try to solve it. Follow the process. Draw a picture, list your variables that you know and the things you're looking for, and then try to use equations of motion. Ready, go. All right, so now that you've got an answer, let's see if it agrees with what I got for you. Here's a picture. First things first. You notice, oh boy howdy, there's a typo in my picture, sorry. Assume that this says 25 meters per second, all right? I changed the problem because I didn't like that the acceleration was exactly half of the velocity. So anyway, let's assume that that says 25 meters per second squared, but we have an initial velocity of 0 over here, a final velocity of 62 meters per second, and some x distance that we don't know. I've labeled positive and negative just as we talked about in the strategy for problem solving. Now let's list our variables. So we look here, we know our acceleration is a positive 25 meters per second squared. Our initial velocity is 0. Let's define that starting spot as 0. And we want to know our final position, knowing that the final velocity is 62 meters per second. Notice I didn't label time. We don't know time, but we don't care. We weren't asked to figure out how much time this is going to take. So I left that off. You could include time as another unknown. But those are our variables. So now to try to solve, I want to pick the equation of motion that does not involve time, since I don't know the time, and instead use this third equation of motion. Since we know both velocities and the acceleration, we can easily solve it for our final position, which becomes the difference of the squares of our velocities over 2a. Plug in our values and we get, look at this, boom, box worthy. 77 meters is the minimum length of the aircraft carrier. And as you can see, like any good engineer, there's always a little buffer zone, a little extra distance, a safety factor, so that if something goes awry, the plane doesn't just plummet into the ocean. So there's an example problem for you all. All right, now what I want to do is move on to looking at things that are moving in the vertical direction. When things are moving in the vertical direction, we have gravity at play. So let's say, for example, I have a coin. I flipped the coin up. It's going to move up. It's going to be at the very peak of its path as it travels, and then it's going to move back down. All right. So question for you. If we ignore air resistance, what is the velocity like in each portion of that travel? Is it positive, negative, or 0? And what is the acceleration like in each part of that travel? Positive, negative, or 0? Let's see, I don't have a coin, but here I have a pen. Let's assume that this is our object, right? So on the way up, at the very peak, and then on the way back down. What are each of those things? All right, hopefully you've thought about it. Now let's talk about it together. Ready? So on the way up, what we have is positive velocity that's slowing down and a negative acceleration. It's accelerating down due to gravity. At the very peak, its velocity is 0, but its acceleration is still down as a result of gravity. And then on the way down, it has a negative velocity as it's moving down, and guess what? Its acceleration is still down towards the center of the Earth as a result of gravity. So what we find, as that example kind of illustrates, is that if we ignore air resistance, all objects always have an acceleration downward towards the center of the Earth, and what we find is it's been proven experimentally that that acceleration towards the center of the Earth is always the same for all objects. So that acceleration, if we're near the Earth's surface, it actually varies with altitude, but let's assume that we're near sea level, near the Earth's surface, that acceleration due to gravity is going to be the same for all objects, and it's going to have a magnitude of about 9.81 meters per second squared. It's like 9.806, so sometimes you'll see me just use 9.8 because that's very close approximation, or 32.2 feet per second squared. So, a couple cool videos that illustrate this idea of all objects accelerating towards Earth at the same time. This is a longer video and I encourage you to watch it, but I'm going to just kind of skip through to a couple points. So this is Brian Cox. He goes to this large vacuum chamber that NASA uses. And so, oh, excuse me, well, going too fast. So they're going to have a bowling ball and some feathers here. They lift them up, and so as you can see, Brian Cox is still in the chamber, so it's got air in it. And when they drop them, we want everything to fall at the same rate, but nope, they don't. The feathers fall much slower because of the presence of that air. Air resistance slows their descent. They do not fall at the rate of 9.8 meters per second. But the amazing thing is, they then pump out the chamber. All the air gets pumped out of there. And now they do their little countdown. They get ready to release. And check this out, a slow motion video. They drop the bowling ball and the feathers, and they descend at the exact same rate. Look at this. I love the audio on this. You should go back and watch this clip because you have these NASA PhD scientists just being awed by this. I've seen this video like 30 times and I still get excited about it. Look at that. Those feathers are falling at the exact same rate as that bowling ball. Boy howdy, that is amazing. So really, really cool demonstration of what's going on there. They fall at the exact same rate. Another cool example of the same idea takes place on the moon during one of the Apollo missions to the moon. Maybe I'll try to let you hear the audio here.
For you, the feather happens to be appropriately a falcon feather for our falcon, and I'll drop the two of them here, and hopefully they'll hit the ground at the same time.
Check that out, a hammer and a feather. Because of the lack of atmosphere on the moon, they drop and fall at the same rate again. Oh boy, howdy. Okay, one more time. I can't help myself. Oh, lost my cursor. All right. Oh boy, howdy. So class, here's another example for you. Believe it or not, fleas, the little tiny insects that pester pets, can jump vertically 22 centimeters. So, based on that information alone, I want you to determine the initial velocity of a flea that jumps 22 centimeters vertically. I want you to figure out its final velocity as it lands back on the ground, and I want you to figure out its hang time. Now keep in mind here, when I say initial velocity and final velocity, you can't just say 0. Yes, it starts at 0, but I want the initial velocity as it leaves the ground. And I want the final velocity the moment it's impacting back to the ground. So pause the video, try this one out. Seems like there's real little information. I want you to try to figure it out anyway. So give it a go. All right, so hopefully you've paused and given it a try on your own. Here's my solution written out for you. So first things first, we need a picture. So I got a picture here of a flea, and what its path is going to look like. Well, it's going to jump up. It will reach 0 velocity at its maximum height the moment that it stops, just before coming back down, and then it'll return back to its original position. Now let's label our variables. In this problem now, what we see is we have 3 different points in time. We have it where it starts here at the ground, we have it when it's at its max height, and then we have it when it returns to the ground. So I'm going to label my variables for all of those points. So my initial spot, I'm going to call 0. starts at 0 meters. Up at the top, it's at 22 centimeters or 0.22 meters. And then when it gets back to the ground at position kind of point 0, 1, and 2, as you see here at point 2, it returns back to 0 meters. What about velocity? Well, it starts with some unknown velocity we're trying to find. Up at its maximum height, it is 0 meters per second. And then when it returns back to the ground, we want to figure that one out as well. And then the whole time it's under the influence of gravity, so its acceleration in the y direction is negative g, or negative 9.8 or 9.81 meters per second squared. Keep in mind here, you see I use the letter g, just represents the magnitude of gravity, the 9.8 or 9.81 meters per second squared. So I have to put the negative to imply that it's in the downward direction towards the center of the Earth. And then there's the time, which I don't know. And t could represent the time from point 0 to point 1, or from point 1 to point 2, or from point 0 all the way to point 2. Since we want the total hang time, I'm considering the time from 0 to 2. So to try to get started now, you have lots of options, right? We want to find this initial velocity. We have the final velocity at point 1, as well as the displacement from point 0 to point 1, as well as the initial position and acceleration. Oh boy howdy, that seems like we should use this third equation of motion. Since we know the velocity at point 1 and we want it at point 0, and we know acceleration and displacement. So I plug in those values. It's 0. 0 squared is still 0. Up at the top, we want v initial. We got negative g as our acceleration. Notice this became a negative because I plugged in the g. y1, which is our 22 centimeters, minus 0. So solving for v initial, it just becomes the square root of 2g times y. So I do the square root of 2g times y, and I get, boom, box-worthy 2.08 meters per second. So the flea leaves the ground with an initial velocity of 2.08 meters per second. So jumping to the answer to part C, by symmetry, what we would find is that the final velocity, when it reaches back here at the ground, it's going to travel the same 22 centimeters under the same influence of gravity. So guess what? It's going to have the same magnitude. The only difference is it's going to be moving down. So the velocity at point 2 is a box-worthy negative 2.08 meters per second, because it's the same magnitude but in the opposite direction. Lastly, to find the total hang time, I will now evaluate from point 0 all the way up and back down to point 2. So I'm going to use that first equation of motion, but now between points 0 and 2. So I need both of these velocities. Velocity at point 2 is negative 2.08 meters per second. Velocity at point 0 was positive 2.08 meters per second. And then we have minus acceleration, which is gravity times time. So rearranging and solving for the time, we should find that we get 0.424 seconds. So a hang time of nearly half a second. So the vertical leap of this flea is probably more than my vertical leap, which is a little bit sad, but pretty impressive if you're the flea. So that's a good example of gravity. You're going to be practicing this a lot going forward. The last thing I want to introduce to you before we call it good to go on Chapter 2 is looking at relationships again with position, velocity, and acceleration. So we've already covered velocity is the derivative of position with respect to time. It's the slope, right? And we said that acceleration is the slope of velocity with respect to time, the derivative, right? So I want to look at that in the other direction, which we'll do in a second. I forgot. I had one other example, conceptual question here for you. So if you took a ball, we'll get to what I was just talking about in a minute, but if you took a ball, threw it straight up at 30 meters per second, and then took the same ball and threw it straight down at 30 meters per second, which of these two would impact the ground at a greater speed? Think about it. I want you to pick one. Or tell me if they'd hit at the same time. So which one is going to hit with a greater speed, or will they be the same? So, fun fact, they would actually impact the ground at the exact same speed, Because the one thrown vertically at 30 meters per second, by symmetry, as we just talked about with the flea, when it returned to that exact same location vertically, it would be moving downward with 30 meters per second, the exact same as the one thrown downward at 30 meters per second. Now the difference obviously is that the one thrown up would take much more time to reach the ground, but they would both impact the ground, strike the ground with the same velocity. Okay, now getting back to what I meant to introduce a second ago. So velocity is the derivative of position with respect to time. Now, what we can do with this is rearrange our equation to say dx equals v dt, and from here, if we use calculus, we can integrate both sides of this equation. Taking the integral of both sides of this equation, we find that the change in position is just the integral of velocity with respect to time. So those of you with calculus experience, you'd understand fully what this integration means. If you don't, a simple way to conceptualize it for the terms of what we're doing in this class is to think of the integral as being the area under the curve. So if we looked at a velocity versus time graph, the total amount of this shaded area would be the integral. And so the displacement would be equal to this area. Now, if you think of area, right, it's units, if you have length times width, you would multiply the units of the length times the units of the width. So here, one axis is velocity, meters per second. Our other axis is time, seconds. When you have meters per second times seconds, you just get meters. So our displacement is the area under the velocity versus time graph. So velocity is the derivative of position, and position is the integral of velocity, both with respect to time. Same thing is true with acceleration and velocity. Acceleration is the derivative of velocity with respect to time. So we can solve and find that the change in velocity, keep in mind the delta, this is the change in velocity, is the integral of acceleration with respect to time. So again, graphically, that's the area under the acceleration versus time graph. Keeping in mind, if you're above the 0 point on the y-axis, you have a positive area, and below it's a negative. So keep that in mind. But again, acceleration is the derivative of velocity with respect to time. Change in velocity is the integral of acceleration versus time. All right. So again, we can use these integral and derivative relationships when solving and dealing with problems involving a changing acceleration and changing velocities with respect to time. All right, so this again is considering when acceleration is no longer constant, you have to use integration. You cannot use those equations of motion we dealt with earlier. So just to recap real quickly, make sure we understand. All right, if you have position versus time, you take the slope at any given point, that gives you velocity. All right, area under the graph doesn't really have any meaning at this point. All right, if you have velocity versus time, the slope is acceleration, the area under the graph is the displacement. If you have acceleration versus time, the slope, the rate at which acceleration is changing, is something known as jerk, how quickly something's jerking as a result of a changing acceleration, and the area under the graph is your change in velocity. So that wraps up all of Chapter 2. Hope you enjoyed, and yeah, let's get pumped for Chapter 3 when we get to talk about vectors.